In this video, we are going to talk about tensor transformations for Cartesian orthonormal systems. So this is sort of the generalization of the video we did in the previous video where we talked about kind of vector transformations in Cartesian orthonormal systems. So this is our overview slide, which we'll spend about 5 minutes going over before we go through each topic in more detail and more examples. In our previous video, we talked about coordinate transformations of vectors, which we can view as tensors of rank 1. And we put this in index notation so we could more easily transition over to tensors. But we said we had a vector, we can take it and represent it in an unprimed basis, and we can also represent that vector in a primed basis, and we use this index notation. So now in this video we'll look at tensors of rank 2 and what we say can generalize to tensors of rank n. So we have our tensor again using our notation. Since it's rank 2, we need 2 indices now instead of the 1 indice we needed for vectors. So we have t sub ij in an unprimed and a primed coordinate system. We will derive this equation and that we can have our unprimed system related to our primed system with these two matrices, ARL and ASM, where ARL are the basis vector in the unprimed system dotted with basis vectors in the primed system. Similarly for ASM. And then we can also do the inverse matrix. And in matrix form, here we have this transformation in index form, but we can also put this in matrix form just because it's a little more familiar. We have our T prime tensor is equal to our matrix A, T tensor in the unprimed system times A transpose, where A is the matrix where we multiply our primed bases dotted with our unprimed bases. And this matrix here is exactly what we had when we had our vectors. We talked about when we changed from one coordinate system to another, we can figure out our matrix, our transformation matrix, with this exact equation here. So this is totally analogous to the vectors, except now we have an A in front and an A transpose behind. And in general, tensor transformations require a factor, this matrix factor, for each subscript in the tensor. In other words, an R-ranked tensor needs R different Aij factors. If the transformation goes from unprimed to the primed system, the sum is over the first subscript. And you can see that here. If you have a system with ijk and some other number of indices, and you want to go to an unprimed system with rs, and I probably should have put t with some other indices, so let me put a little t here, since on this side I have 3 indices. I want on the other side to have 3 indices as well. Then you see that I'm going to have 3 of these matrices, A sub IR, A sub JS, and A sub KT over here. Similarly for the inverse. And then also we have this other alternate expression for A sub ij, and this also should be familiar because it's similar to the expression we did when we did coordinate transformation of vectors, when we did not have necessarily the bases written out, but we had relations between x sub I in the primed system and x's in the unprimed system. We will do an example using Ohm's law to get a matrix of transformation from one basis to another. For our final point, unlike matrix equations where all terms must be in the same basis, the tensor vector notation allows equations to have mixed bases. One other comment I am going to make, I am doing tensors of rank 2, which are matrices or can be represented with matrices, so it's nice to see the representation, but I do put a lot of emphasis on the index notation. Your book actually puts a lot of emphasis on the index notation because as you go to higher ranked tensors, you're not going to be drawing arrays of matrices. You're going to be using this index notation. So it's something you really want to get used to. The first thing I have for you is kind of a little review, or this here for your reference from our previous video, which we looked over coordinate transformation of vectors in a Cartesian system. And we had this transformation matrix A, or A sub ij, that would take a vector in an unprimed system, coordinate system, to a vector in a primed coordinate system. And we were looking for ways to find this transformation matrix A sub ij. And the first way we looked at is if we had the basis vectors for both coordinate systems, we did this the hard way, and then we did this the easy way, where our transformation matrix A sub nm is the basis vector n prime dotted with the basis vector m unprimed. So that's how we found our matrix component by component. And there was the second way, and I'm going to move this because I want it to line up. There was a second method of determining this matrix, and that was if we didn't have the basis vectors for the prime and unprimed system, we might have coordinate equations relating the two systems. So in other words, here we have the x of I coordinate in the unprimed system, and it'll be equal to some formula of x of I in the primed system. And this is how we got each of our components, A sub ij. You can see we took the x of I in the prime component, which is a function of x1, x2, x3. Remember, we have some sort of formula relating the two, and then we took this formula and we took the partial derivative with respect to the j component of the unprimed system. And this again is to get the A sub ij component. I have this sort of summed up here. So remember, vectors are tensors of rank 1. So we have our vector, and we can write it as in terms of our unprimed bases, so coordinates in our unprimed bases, and that should equal to coordinates with our primed bases. And like vector transformation, a vector expressed in a primed and unprimed system is still the same vector. That was the big idea of a tensor. Likewise, the expression for a second-rank tensor in the two systems must obey the following. So here, now we're going to consider a second-rank tensor, and our second-rank tensor expressed in terms of an unprimed basis will be equal to our tensor, second rank because we have two indices, and our primed bases. So it's the same sort of relation. And in fact, our transformation matrix, so to go from an unprimed to a primed system, is this matrix ARL and ASM, where ARL, if you look at this, these are the unprimed bases dotted with the primed bases, much like this over here, the A and M were for vectors. The difference is now we have this matrix twice. So in matrix form, this is going to look like our tensor in the primed bases is equal to A times the tensor in the unprimed bases times the matrix A transform, where A and M, now we have exactly, we can use the exact same form over here as we had for our vector, which is good because really the vectors of rank 1 should be a generalization of higher ordered tensors. And we can derive this form here by writing our tensor and saying, okay, we have our tensor written in our unprimed basis, and then we have our tensor written in our primed basis. So we'll start here and derive this, this transformation matrix. And the first thing we're going to do is dot both sides of this equation here with another basis vector E sub L from our unprimed system. Remember, at this point, our T sub ij and T prime sub rs, these are just components, individual components, sort of like our matrix, our A sub ij or A sub nn. It's just a scalar. So we can move it out and we can group together our direction vectors. So we'll have our EL dot EI times our EJ, right? Because we dotted it, so we can move the dot in here times EJ. Again, we can move the dot in here, dot it with ER, and then we multiply times ES prime, because this is a multiplication. When we dot these, remember these are basis vectors, so it's equal to 0 when L does not equal to I, and it's equal to 1 when L equals I. So we can replace this with our Kronecker delta Li. I was going to say similarly, but actually we can't do that here because here we have a basis vector in the unprimed system and a basis vector in the primed system, and these are not necessarily orthonormal, but we can replace this and just call this our matrix A sub RL. And then on this side, since we have our Kronecker delta, that means L must equal to I. So at this point, we're going to replace this I with L and get rid of our Kronecker delta. So far, we have something over here in our unprimed system equal to something in our primed system with this little matrix in between. But we don't have one tensor right now equal to another tensor times matrices. But we can do that same trick. We can multiply again, or dot multiply, by another basis vector. So we will multiply by EM. Again, we're going to do the same trick, another basis vector in our unprimed system. So multiplying both sides by the bases. Again, we can pull out our scalars, our T sub Lj and our T prime of Rs, and then we can group our two basis vectors together here, and here we group our two basis vectors together. Same trick on this side. These are orthonormal bases, so we can replace it with our Kronecker delta Mj. And again, over here, actually this should be an S prime. I missed that. So these are not necessarily orthonormal because this is from the unprimed and this is from the primed system, but we can replace it with this matrix A sub Sm. Again, the Kronecker delta means that M must equal to J, so we can replace this J with M. So that tells us our tensor, our Lm component of our tensor in the unprimed system is equal to the primed system, Rs, times these two matrices. And we said that our first matrix, ARL, where did we get that here, was dotting the Lth component in the unprimed system with the Rth component in the primed system. So it just kind of reversed the indice, where L is unprimed, R is primed. Similarly, over here, when we did our ASM, that came from right up here. We dotted our mth, so this second component is our unprimed, and our first component is the primed system. So actually these two matrices are the same. It's just that we just happen to rename the R to S over here and the L to M over here. And of course we wanted to use different indices here because we don't want to mix them up, but you can see they actually end up doing the same thing. Each of these matrices for the SM component takes the second component from the unprimed and then dotting it with the first component in the primed system. And in matrix form, we would write it this way. So we'd have our T prime is equal to our matrix A times our T tensor in the unprimed system times A transpose. In matrix form, we would write that as our tensor in our primed system is equal to our matrix A times our tensor in our unprimed system times A transpose. And for rank 2, I wanted to give you an example. Remember, rank 2 has two indices, so it's quite naturally represented by a matrix, right? So your I component versus your J component. And we discussed briefly the stress tensor before, where here we have different stresses. There are three stresses, so this is the first stress in the first row, the second stress in the second row, the third stress in the third row, and the columns are the directions that the stresses apply to. So the stress, this first type of stress, this is what happens in the x direction, or how it affects the x direction. This is how it affects the y, this is how it affects the z. And the idea is you can't sum up, even although these three terms here in the first column represent all the stresses in the x direction, this column represents all the stresses in the y, and this represents all the stresses in the z. You can't just sum these up because the nature of the three stresses are different. So you'll have to have different coefficients for each of the three. So therefore you get this stress tensor. So that is an example of a 2 by 2 matrix. And you know what? I'm going to use the same matrix, but I'm going to plug it in because actually we don't have any numbers, into our conductivity matrix. That's the one that your book uses a lot. And so let's briefly go over that, and then we'll try a transformation matrix for this second-rank tensor. So the conductivity matrix is based on Ohm's law, or is Ohm's law. So here we have J, our sigma, and our E. And just to go over some of the physical meaning, the J vector is the current density, the E vector is the electric field, and the sigma is the material's conductivity. And so this could be easily written as a single sigma if sigma were in fact a scalar. And it will be a scalar in kind of the simple case where the amount of current flow is governed solely by the magnitudes of sigma and E, while the direction of the flow is always parallel to E. However, there are many non-isotropic materials that have different conductivity in different directions, in which case we need this conductivity matrix. So our sigma of 1, 2 describes the flow in the one direction, or the x direction, due to an applied field in the 2 direction. In this case, we think of x being 1, y is 2, and c is 3. So really, to define this here, the conductivity as a tensor, we need to include the bases. So we're going to define the tensor, and we have the 2 lines on top to show that it's a tensor, and it's not just this matrix, but we have to include the bases. So we're going to say we're in an unprimed basis E sub I, E sub j. And now we can write our equation here. We have our J vector is equal to our conductivity tensor times E, our electric field. And then converting this to index notation, I actually did a couple of steps here. So our J component in the x direction is equal to our conductivity tensor element JK. And in this case, here are the 2 bases vectors that go with the conductivity tensor, e to the j, e to the k, or e in the j direction, e in the k direction, and then I multiply times my electric field in the L direction. So this basis vector goes with e to the L. I probably should have grouped them together and then rearranged them, but remember, I can rearrange them because in this case, by the time we get down to the sigma of jk, that's just a scalar. So here we have our equation written in index notation using our tensor. And what I want to do is show that this equation here, using our index notation, will come out with the same equation we would have gotten with the matrix, just to show you that it's not anything different. So working over here, we have our 2 bases vectors multiplied, but we dot it with E sub L. So I can group these 2 together, dotting E sub K with E sub L. They're both in the same unprimed system, so they're orthonormal, because actually I should say that we have assumed that they're orthonormal. We assumed that over here when we started our topic. And also, don't forget, if you don't have an orthonormal system, you can make it orthonormal by using Gram-Schmidt, which is why we like Gram-Schmidt. But anyway, so here you are. Since it's orthonormal, we can replace the KL with this Kronecker delta KL. And then what can we replace over here with the Kronecker delta? Well, we can replace this L over here with a K and get rid of the Kronecker delta, which is what we did over here. I want my J sub I component, so I'm going to multiply this by my E sub I basis vector. Since these are orthonormal, it's going to equal to 0 except when I is equal to S, in which case it's equal to 1. So here I'm going to substitute J sub I instead of S. And on this side of the equation, I'm going to get E sub j dotted with E sub I. That means it's 0 except when j equals I, which means I can replace this j here. Well, this becomes the Kronecker delta, and then I can replace this j with I. So I get our sigma ik e to the k, which is exactly what we had over here, except, instead of J indice, we have K indice, but it's really the same. So we have the same form as our matrix multiplication, which is nice, it's consistent. The next thing I want to do with my conductivity matrix now is suppose we want to compute the components of the conductivity matrix in a second Cartesian basis, that is in a prime basis. So I want this same conductivity matrix, but now instead of E1, E2, E3, I want E1 prime, E2 prime, E3 prime. So I'm going to have my sigma 1, 1 prime, sigma 1, 2 prime, sigma 1, 3 prime, etc. So in effect, we're getting to the transformation, the coordinate transformation of this system. And by my formula over here, what I expect is this prime tensor should equal to my AMN multiplied by my unprimed tensor times my ANM transpose. And then using my formula for A and M, it will look like, so A11 is going to be E1 prime dotted with E1. So that's what I have here. A11 is E1 prime dotted with E1. A12 coming back up here. A12 is equal to E1 prime times E2. That's this component here. Let's just go to this one here. This is the 2,1 component. A21 is E2 prime dotted with E1. And that's exactly what we have here. So this formula here, along with this matrix, will give you the transformation from your old bases, your E1, E2, to your new bases, E1, E2, E3 prime. Also, just a quick note. So this notation is actually the same as this this matrix here. These two matrices are actually the same. It's just that in this case, the R index is renamed to N, and the L index over here is renamed to M. And the reason why I brought this up is because I wanted to be consistent with the last video where we were doing vectors, but they're really the same. Just rename R into N and L into M, right? So ARL becomes AR, so that's N, and L becomes M. So A of MN here is equal to EL. So EL, that would be EM hat dotted with, and then I need ER prime, and R is N. So that's going to be EN prime hat, which is exactly this since the dot product is commutative. So they're the same formula here. I just wanted this to be consistent with our last video when we did vectors as our rank 1 tensor. Okay, as I mentioned, what we just did is we took our rank 2 tensor, our matrix, the tensor represented by a matrix, and we converted it from an unprimed basis to a primed coordinate system, a primed basis. And you can see the similarity with the vectors, because with the vectors we use this matrix to go from one vector to the from the vector in the unprimed to the vector in the primed. Here we use this matrix twice, as A and A transpose. If you have, you can generalize this. So we did this for rank 2, but if you have a tensor of rank R, then you're going to need R A sub I j factors. Our last topic, so I did this using matrices because it's easy to see, but I did also write out the indices form of your tensor. And as you go into higher ranked tensors, you know, you can't necessarily do arrays of matrices and expect to manipulate them. So at some point you really do want to get used to these indices. And there is something that's nice about them, and that is, unlike in a matrix equation where all terms must be in the same bases, the tensor's vector notation allows equations to have mixed bases. And let's look at the Ohm's law as an example, but we'll start with a fresh page so we have more space. So I've cleared out some space. Here are my general notes about tensors, and then our statement, unlike in a matrix equation where all terms must be in the same bases, the tensor vector notation allows equations to have mixed bases. So here I've written J, our J vector, as a, in our unprimed bases, and then I wrote it again in our primed bases. E also has a representation in our unprimed bases and in our primed bases, and then our conductivity tensor, it has a representation in our unprimed bases and also a representation in our unprimed bases. So we can put any of these into our Ohm's law equation, where the vector J is equal to our conductivity dotted with our electric field. So E can come from our primed or unprimed, and we can write it in the same equation with our conductivity in primed or unprimed, in the same equation with J in primed or unprimed. So again, any combination of representations in the equation can be used. So here I can say have my J in my unprimed, and that's going to be equal to my sigma can be in primed, and then my E can be in my unprimed. And what happens is the dot product of these basis vectors will take care of everything, because here you're going to have, again, your conductivity and your prime system, your E, your electric field, and your unprimed system, but then you're going to have this E sub j and your E sub k dotted with this E sub l. So I can take my E sub k and E sub l, that will give me, remember, my transformation matrix up here. And so basically the basis, because you're carrying around your bases with you, when you write this all out in terms of your bases, your vectors and your tensors, in terms of your bases vectors, you'll end up with the transformation matrix will kind of just appear for you. So again, over here in this example, the fact that our conductivity tensor from the primed frame are combined with components of E from the unprimed frame represents no problem. The dot product of the bases vectors take care of the mixed representation as long as the orders of the bases is preserved. Oh, just do notice, like when we have this dot, the E sub k gets dotted with the E sub l. We don't reach over here and dot the E sub j with the E sub l. We have to preserve the order. And the value of expressing the tensor in this form should now be clear. In the addition of handling the same algebraic manipulations as a matrix array, that's something we demonstrated, it also contains the information necessary to transform the elements from one coordinate system to another. So that's a tensor is truly a coordinate independent geometric object. So this is what we mean by a tensor. When they give you that confounding definition, a tensor is something that transforms like a tensor. To review what we've covered in this video, we went back and reviewed how we transformed vectors, which are tensors or represent tensors of rank 1, from one coordinate system to another. And we had this matrix here given to us by A sub nm, E, the nth basis vector in the prime system dotted with the mth basis vector in the unprimed system. And we compared that. We started looking at rank 2 tensors, which are matrices. So our tensor notation, since it's rank 2, it has two indices, I, j, again, because of the two indices, naturally represented by matrices. And then with tensors, we always carry the bases with us, E sub I, E sub j. And we can transform that into another primed basis vector. So that'll be our tensor Rs in the primed coordinate system with our basis vector ER prime and ES prime. And we found that this can be transformed here so that our unprimed system is equal to our prime system times this ARL matrix, and ASM matrix was where ARL is the Lth unprimed dotted with the Rth primed. And we saw that this is the same equation. I told you that it's just the R becomes an N and the L becomes an M. And I showed you these are the same equations that we got when we did our vector transformations. It's just that now for the rank 2 tensor, we have we need to have two versions of our matrix A, which is over here. So in general, tensor transformations require this transformation matrix factor for each subscript in the tensor. In other words, here you have two subscripts, you need two versions of A. And an Rth rank tensor needs R different factors. We looked at a rank 2 tensor. We used the conductivity tensor to take a look at that, see what the tensor looked like. It was a matrix. Then we did the transformation matrix, or we saw how to use this transformation equation and find the matrix. last, there's this note. So it was important. So even though we used a lot of matrix notation because that was what is kind of familiar, we also made sure we saw the same calculations using this tensor notation. The tensor notation becomes more important as you go to higher ranked tensors, because you really don't, like, how do you manipulate an array of matrices? So you need to start getting used to manipulating these indices. But actually, we found that when you, there's another advantage, and that unlike a matrix equation where all terms must be in the same bases, the tensor vector notation allows equations to have mixed bases. And what we did is we took this in Ohm's law. We took our vector j and we put that in a standard basis. We took our conductivity tensors, we put that in the prime bases, and then we took our electric field and we put that in the standard bases, and that was okay. What we saw is we want to preserve the order of bases, but what we saw is the bases then, when we group them together, we do this dot product. Here we have the dot product of an unprimed and primed. That gives us our matrix, right? Our transformation matrix. So by carrying around the information about the bases and then doing this dot product, the transformation matrix comes up automatically. So that's it for this video. Thank you for watching.